Okay, so I think we can get started. Hello, everyone. Welcome to the first section of the network models. And I think I have already met you guys in the Monday class. So let me introduce myself again, and I also tell you my office hour. My name is James Kang, and I am a second year AMS master student. Last year I took this course. So the thing is that last year I took this course, but this is my first time to be a TA. And the other TA, he had not taken this course, but he has experience in being a TA. Okay, so that's the truth, but whatever. So if you have any questions, just feel free to contact me. And my office hour is Wednesday from 7 to 9 p.m. And actually, this is a huddle room. So Dr. Costello told me that our department want our TAs to hold our office hours in person. So if you have any questions, just find me in this place every Wednesday from 7 to 9 p.m. Or if this time does not fit to you, you can just shoot me an email and we can make an appointment. Okay. So if at the beginning of this class, if you had downloaded the syllabus, you will see that this class should be about MATLAB. However, I suggested to Dr. Costello that last year when I took this class, the TA used just one section to talk about very basic operations in MATLAB, which I think is very useless. Because if you have no knowledge in MATLAB, after one section, you still cannot program it, right? But if you have some knowledge in MATLAB, this lecture is useless to you. So I suggested Dr. Costello to talk about something related to proof, because after I reviewed my homework last year, I found that half of the problems were about proofs, and the other half of the problems would be, so please show us the process of some algorithm, which you can either write a program and run it and print out the result, or you can just do it by hand because the problem sizes are very small. But since half of the problems are about proof, so it is very necessary for me to talk about the rigorous proof to you in case that you have not taken some courses like fundamental concepts of mathematics. Okay, and also another thing is that I will also help you to review some basic graph theory, because if you take a look on SIS, you will see that the prerequisite of this course is called Introduction to Optimization, right? However, the reality is that, oh, please take a seat. So the reality is that for many courses, the prerequisite on SIS is just a nominal prerequisite, but it may also have a real prerequisite, and the real prerequisite may be different from the nominal prerequisite. So for the introduction to optimization, I think the majority of the contents should be about continuous optimization. But for the contents in this course, I think it is more related to combinatorial optimization. So if you have very strong interest in combinatorial optimization, I would also recommend you guys to take a course. I don't remember the course code, but it is just called combinatorial optimization. It's a 700 level course in AMS department taught by Dr. Amitabh Basu. Yeah, I would strongly recommend that course to you if you have interest in combinatorial optimization. Okay, so as I have said, today's class would be about rigorous mathematical proof, and I will also help you to review something about graph theory. And if we have extra time, I will also help you to review some basic search algorithms like depth-first search or breadth-first search. Okay, so let's get started. Okay, so first I want to say when you are doing a mathematical proof, what you are doing is to prove a statement or disprove a statement. So a statement, it is a sentence of which it is meaningful to say whether the content is true or false. So for a statement, we always use P, Q to represent it. But please, so for a statement, it can be true or can be false. Like a graph G and A has no cycle. This is a sample statement. Oh, by the way, so in this course, we use N, which means nodes, to represent the node set, and A, which means the arcs to represent the arc set. However, if you also take the combinatorial optimization class, they will use different notations. For nodes, they will say it is a vertex, and for arc, they will say edges, but they are interchangeable. But if you are doing the homework in this class, so please use node and arc, right? So this is a small difference, but in reality, they are interchangeable. Okay, so when it comes to the statements, we have some relations like, this is called P and Q, and this is called P or Q, and this is the negation, not P. So I think many of you guys should have already learned it. So so can anybody tell me what is the sufficient and necessary condition for P and Q to be true? Can anybody tell me? When does P and Q is true? Yeah, right. So P and Q is true if and only if both of them are true. Otherwise, it is false. And how about P or Q?
Wow.
Yeah, right. So P and Q is P or Q is true if and only if either one of them is true, or they can both be true. If they are both wrong, if they are both false, then it is false. Okay, so the negation of P is just not P. So if P is true, negation of P is false. If P is false, then negation of P is true. Okay, then I think in almost all the proof questions, the question may ask you to prove this or this. So this is called implies. So we can say if P implies Q, or we can say if P then Q. So that's to say we need to show what P is true. You want to show that Q is true. However, for this one, you need to be very careful. This is called P is equivalent to Q, or say P if and only if Q. So it is also written as P if and only if Q. P if and only if Q. So if in the homework problems, it asks you to show some statement if and only if the other statement. When you are writing your answers, please be very careful that you need to prove both directions. You need to prove P implies Q and Q also implies P. And I know that there exist some cases in which your answer is actually correct, but some marks are deducted. This is possible. That's because maybe the TA made some mistake, but I think the best way to avoid this circumstance is to be very clear. So if the problem asks you to show P if and only if Q, then please just state, okay, so first we want to show this is the only if part, and then we show the if part. Be very clear. Okay. So this is about some basics, and then we want to talk about some proof techniques. So the first one is about direct proof. This is very straightforward. So if the proof asks you to show P implies Q, then you can, this is the easiest case. Let's say an example. Can anybody tell me how to show this statement? The sum of the degrees of all the nodes in a graph is even. Can anybody tell me how to use direct proof to show this? Oh, please.
I think the sum of the degrees is just 2 times the number of nodes, because like it just thinking about like every edge has 2 ends, so like it's kind of twice. Like,
so it is 2 times what?
The number of nodes.
Is it the number of nodes or the number of arcs? Because you have said one arc is connecting 2 nodes.
Oh yeah, it's like number of arcs.
Right, you are right. So if we use direct proof to show this statement, because we know that for every arc in a graph, it connects 2 nodes and creates 2 degrees. So the sum of the degrees of all the nodes in a graph is just 2 times the number of arcs. Okay, this is very straightforward. And the second one is proof by contradiction. This technique, I think, when I learned this, when I studied this course, I use this technique very often. So proof by contradiction is that you want to show P implies Q. So first, you assume P is true. And then you suppose Q is false. You want to find a contradiction. Let me also give you an example. Wait, so did Dr. Costello told you the concepts of tree forest in the last lecture? Okay, perfect. So let's see this example. So in this example, it says a tree has exactly 1 path between any pairs of nodes, right? So can anybody tell me how can we use proof by contradiction to prove this statement? Or I give you some hints. So if you want to prove a contradiction, you may first transform this statement into P implies Q. Then how can we transform this? That's to say, if a graph is a tree, then it has exactly 1 path between any pairs of nodes, right? So P is a tree, Q is exactly 1 path. Then how can we prove by contradiction?
Assume it doesn't have 1 path.
Okay, so assume
it doesn't have 1 path between any pair of nodes.
Okay. Then where's the contradiction?
My question is if this graph is directed or not.
Oh, you may assume that it is an undirected graph.
Undirected. Okay.
Yeah. Right. Assume that this is on the. Oh, please.
Offer a solution.
What?
Can I offer a solution?
Sure, sure.
So since it's a tree, it's acyclic.
Right.
And if it has more than one path, then that means that you're create a cycle because you just follow a path, follow a path, and then it's not a tree anymore.
Okay. Okay. So that's to say your contradiction is that because we assume that this is a tree. However, if there are more than one path, then there must exist a cycle. But it is a contradiction with the tree, right? Okay, perfect. Oh, by the way, so if you want to say something, just shout out. No need to raise up your hand, because I think the difference between a section and a lecture is that in section it is free for discussion. So that's the reason why we split the class into many different sections. Okay, then I want to talk about a very similar thing with by contradiction, but not the same. So it is proof by contrapositive. So proof by contrapositive means that you want to show P implies Q. But you just show not Q implies not P, not P. So my question is, if we also want to show this example, how can we show by contrapositive? Not by contradiction. How can we show it by contrapositive?
So for a graph such that it doesn't have exactly one path between any pairs of nodes, then it's not a tree.
Wait, so say slowly.
For a graph that doesn't have exactly one path between any pairs of nodes, it's not
Because
a tree.
you are so what are you negating? You are negating exactly one path between any pairs of nodes. So what is the negation of this statement? It should be there exists at least one pair of nodes such that there are more than one path between them, not any. So that's to say, if you are negating for any, if you are negating this, you need to transform it to be there exists at least one, right? So be careful with this when you are proof by contrapositive. Okay, but in general, you are right. So you are saying that if there exists at least one pair of nodes such that more than one path between them, then this cannot be a tree, right? Is that what you want to say? Okay, thank you. Yeah, so here I want to, because you see that for proof by contradiction and proof by contrapositive, I use the same example. So that's my aim. I want to tell you the difference between 2 and 3. That's to say proof by contradiction and proof by contrapositive. So let me emphasize once more. So you want to so for proof by contradiction, you show P implies Q by showing P and not Q is false. Remember what we talked, because you are trying to find a contradiction when you are assuming that P is true and also not Q is true, and then you want to find a contradiction. The process of finding a contradiction is to show that P and not Q is false. But for proof by contrapositive, you are showing that P implies Q by showing not Q implies not P is true. So when you are doing the proof, if you want to show by contradiction, please do not mess it up with proof by contrapositive, because I see that some students cannot distinguish between them. So now you understand the difference between them. And if you want to show either by contradiction or by counterpositive, please state in the first line, say, proof, we show by contradiction or we show by counterpositive. So that's what I said, to be very clear. Okay, so then I want to ask you guys a question. Why does proof by contradiction make sense? That's to say, why can we prove by contradiction? Or in other words, why does P implies Q? It is equivalent to P and not Q. Can anybody tell me why? Why does proof by contradiction make sense? Oh, please.
I remember when I was studying discrete math, there was like a table where if you have like true, false in them, and then it turned out that like these two statements are equivalent. So
right.
For like all four cases of whether P and Q are true and false, like they're equivalent.
Yeah, that's exactly what I want to say. So what I want to emphasize here is that P implies Q. We know that PQ are both statements, so they can either be true or false. And the whole statement P implies Q, whether it is true or false, it is equivalent to not P or Q. I wonder if this is what you want to say.
Yes.
Whether it's true or false is equivalent to not P or Q, right?
Yes.
So can anybody understand why they are? Can everybody understand why they are equivalent? Okay, perfect. So that's to say, P implies Q if and only if not P or Q. So that let me see. So you want to show that P implies Q is true, then that's to say not P or Q is true. And what you are showing is that we want to show that this is true, and this is also true. Then what is then the negation of not P or Q is P and not Q. So you are showing that P and not Q is false. So that's the reason why proof by contradiction makes sense. So that's it. So what here I want to share with you. So if you are doing research and when you want to prove something, please check your assumptions very carefully, because sometimes people may assume something that is false, and then they say that, okay, I have proved something. However, it turns out they are wrong because their proof is based on a wrong assumption. Okay, so and excuse me, what's your name?
Roma?
Okay, as you have already said that, so there's a table saying that, okay, so if P can be true or false, Q can be true or false, and we have many possibilities of whether P implies Q is true or false. Mm-hmm. And we see that P implies Q, it is equivalent to not P or Q. Then if you are based on, then if your proof is based on a wrong assumption, that's to say P itself is wrong. That's to say not P is true. Then whenever you want to, whatever you want to prove, because not P is already true, then your proof does not make sense because this guy is always true, right? Can everybody understand what I'm talking about?
Wait, if P is false, then isn't the statement vacuously true?
If P is false, then not P is true, right?
Yeah, but if we're starting from a false statement, then anything derived from it must be true because it just doesn't make sense.
Yes, right. Anything right must be true. So let me give you an example, very simple example. So P is that it is raining outside. Q is that the ground is wet. So if it is not raining outside, then the ground can either be wet or dry. Because if you just pour some water onto the ground, it is still wet, right? Okay. So the first one. This is not that common compared with the first three proofs. That is proved by an algorithm, or say algorithmic proof. So in this kind of proof, you come up with an algorithm to prove something. So let me just review an example that you have in your lecture. Okay, so you have this example in your lecture notes, a tree of, but of course we assume that it is undirected. I want to show that a tree has at least 2 leaf nodes. Can anybody tell me how can we come up with an algorithm to show that a tree has at least 2 leaf nodes? Can anybody tell me? By the way, did Dr. Costello told you how to prove this in her lecture?
No.
No? Okay. Okay, so I'll tell you how to prove. Okay, so our algorithm is like this. It's an algorithm. So first you pick a node X. Just randomly pick a node X. And then we can generate a path from X. Because we know that X is a node and this tree, of course, it is a connected graph. So the X must have at least 1 degree. So we can always start from S and try to generate a path. Okay, so let's say, suppose we first find a node V2. Okay. So if V2 has an arc not on the path, that's to say, let me just give you an example. So this is our X, and we start from X to, let me just, sorry, this should be a tree. Okay, so you first find V2, then this arc is on your path. And then if V2 has an arc not on the path, let's see, this arc is not on the path, this arc is also not on the path. So let's see, we pick this one. And then suppose we have arrived at V3. And then we repeat. That's to say, whenever we go to some node, we try to find if this node has an arc not on the path. Okay, so now we have already arrived at V3. Then we see that, okay, so V3, there are 3 arcs that are adjacent to V3. And among the 3 arcs, 2 of them are not used on this path. So let's say we just pick this path. And then we'll arrive at V4. Then at V4, we see that there's no remaining arcs in V4 because V4 is only adjacent to 1 arc, and this arc is already on this path. Then we have to stop. So that's to say, until we reach, let me think of a notation. We reach some V, let me, Vi such that we repeat this process until we reach some VI, such that there's no unused arc, just like, so we start from X, V2, V3, V4. Okay, then we stop. So what can we say about VI? What can we say about VI? Is it a leaf node or non-leaf node? What can we say about VI? Yeah, it is a leaf node. Because once you reach the VI, you see that apart from the arc that you have just used to reach VI, there's no unused arc. So this tells us that VI is a leaf node because VI is just adjacent to one arc. So VI is a leaf node. Then what can we say? If our X is already a leaf node, like what we have shown here, then we are done. Because X is a leaf node. VI is also a leaf node. We are done. So that's to say, if X is a leaf node, we are done. Otherwise, what should we do? Let's say if X is not a leaf node, say we have, now X is not a leaf node. What should we do next? Say we have already found this is a leaf node. We already have one leaf node. Then how can we pick another leaf node? Should we do the same thing again? That's to say, we start from VI and do the same thing as we did from X. So that's to say we start from VI and just disregard those paths that we have used. That's to say, we start from V4 in my case, and then we do the same thing. So that's to say, we pick an unused arc. So we reach the V3, and then we pick an unused arc. Let's say this one. Then we reach V5, and we see that okay, there's no unused arc for V5. Then we can say that V5 is also a leaf node. Then we are done, right? But of course, the algorithm that I've written here is not that rigorous. It's not complete because I just want to show you how to do this. But if in your homework you want to write an algorithm to show that okay, so this statement is true. Also, please state very clearly. Say when you repeat what? Because when you repeat, this is like a while loop, right? So you need to say, oh, we repeat step, say from step 2 to step 4, so something like this. Okay, so is that clear?
What is the definition of a leaf node?
A leaf node. Oh,
When you
isn't
talk
that
about
stated on?
definition of a leaf, then I'll leave.
Oh, a leaf and a leaf node is the same.
Okay.
That's to say, on a tree, a leaf node means that a node that is only adjacent to one arc.
Okay.
Right. It is just like a leaf. So think about a leaf in a real tree. Okay. So the last type of proof is to prove by induction. I think every one of you should be very familiar with it because proof by induction was used in senior high school. Okay, so let's just review them. So you want to prove Pn. P is a statement which is related to n. N is something related to the problem size where n is, say, it is a natural number. Then, first the base case. You want to show that P1 is true. And then you do the induction hypothesis. Oh, by the way, so when Dr. Costello write during the lecture, she will just write IH. So if you see her writing IH, know that it means induction hypothesis. Okay, so induction hypothesis is that suppose Pk is true, where k should be something greater than 1. And then you do the inductive step. In the inductive step, you suppose Pk is true, then you show that Pk plus 1 is also true. Okay, so this is about mathematical induction. And let's see an example. So the example is that if we have a graph GNA with n greater than or equal to 1. If this is a tree, then was this also stated in the lecture? As to say, if we have a graph, an undirected graph, and this graph is a tree, then it should always have n-1 number of arcs. Did Dr. Costello prove this in her lecture? Okay. So that's to say my section is complementary to her lecture. So if we want to show that a tree has n-1 arcs, what should we do is that we can just by induction. First, we see the base case in which n equals to 1. Then when n equals to 1 and it is a tree, this is just a singleton node. So this is the trivial case, right? And n-1 is just a 0 because this is a singleton node. So trivial. And then induction hypothesis. That's to say, when we have k nodes, and then we suppose there are k-1 arcs, then what can we say in the inductive step? So we are assuming that when when there are k nodes in this tree, and we suppose that this tree has k-1 arcs, what can we say? What can we say in the inductive step? Can anybody tell me?
When n equals k plus 1,
Okay.
you need to prove that absolute value or number of edges is k.
Then how? How can we show that? Okay, let me write what we just said. So when n equals to k plus 1, then please continue.
Yeah, suppose then we need to prove that
Want to show a
equals k.
right. this is what we want to show. Then the main problem is how can we show that? Some hint. Remember, we have already proved that for any tree, there are at least 2 leaf nodes. So you can start from the leaf node. How can we show that this tree must have k arcs?
Can we start from any random leaf and then say that we add one more regardless of where it is, as long as one more, we have one more node, there has to be at least, like there has to be one more edge.
Yeah, almost right. So so that's to say, because we know that it is a tree, so we can pick any leaf node, and we know that there must exist at least 2 leaf nodes. So we pick any leaf node, say it is V. Okay, so we have already picked V. Then if we remove V, then how many nodes are remaining in this graph? We have already removed V. Other students, can you tell me? If I remove this leaf node V, then how many nodes left? Yeah, n-1. Then according to my induction hypothesis, how many arcs are there in this remaining graph? And we know that this remaining graph must be a tree, right? Because we have just removed a leaf node. How many arcs left? Yes. Then if we add back V, we have k-1 arcs, right? Okay, so let me complete. If we remove V by the induction hypothesis, k-2 arcs remain. Then if we add V back to the tree, we know that there are k-1 arcs. Okay, we are done. This is about proof by induction. So I see that we still have okay. So these are all that I want to say about proofs. So we have reviewed direct proof, proof by contradiction, proof by contrapositive, proof by induction, and algorithmic proof. These are all the common techniques in proof. And because we still have 5 minutes, I want to quickly help you to review some search algorithms. So last night, when I reviewed the lecture notes of this course, I see that Dr. Costello didn't talk much about the search algorithms. By the way, so let me check. How many of you have already learned data structure and algorithms? Raise your hand. No? Oh, and how many, if you don't have any programming experience, please raise your hand. You don't have any programming experience?
A little bit of MATLAB.
Oh, no, a little bit of MATLAB, right? Have you learned something like object-oriented programming? No? Okay. So it is about MATLAB. So you may come to ask the other TA, Citron, about questions if you encounter some problems with MATLAB, because my first language is Python. So I think the other TA's office hour, one is that it should be on Monday, and the other one should be on Tuesday, because he has split his 2 hours office hours into two 1 hour office hours. So if you have any question related to MATLAB, just ask him, and he should hold his office hour in his office because he's a second-year PhD student. Okay. So first is DFS. This is depth first search. Because we are about to run out of time, so I will be fast. So depth first search. So think about this. Suppose this is a mountain. This is not delta. This is a mountain. So suppose this is a mountain, and in this mountain there's a diamond. How can you efficiently search for this diamond? One way is to in this manner until you find this diamond, right? And the other way should be you just search layer by layer until you find this diamond. So this is the core idea of depth first search. And this is the core idea of another kind of search algorithm. It is called breadth first. I'm not sure if I spell it correctly, but or whatever. First search. Okay, so that's it. So I will quickly tell you how to do DFS. So in DFS, we use the main idea that we use is to do a recursion. So suppose now you want to explore this vertex V, or say this node V. And what you need to do is to first, So first we need to maintain something called visited. It is like a hash map. And for every node, we first mark them as false. False means that we have not visited it. So from V1 up to Vn, it is false. Okay, then if we want to explore some node V, what we do is that first we mark it as true. That's to say we have already arrived at this node. And then what we do is that for each VU in the arc set, that's to say for all the nodes that are adjacent to V, if U is not visited. So how to check if U is visited or not? You check this hash map. So if not visited U, that's to say if U is not visited, then you call explore again, explore U. So remember that this is a function, this is a how to say recursion. This is to explore. And then what we do for depth first search is that we function DFS. Suppose we have a graph G. And then for each node, we first mark them as unvisited. That's to visited V equals to false. And then for each V in, that's to say for any node, if we have not visited this node, we call explore. Sorry, we have already run out of time. So next, in the section of next week, I will complete my talking about DFS and DFS. And then we'll also talk about simplex algorithm, which is widely used in linear programming. That should be the content for next week. So next week, I will elaborate more on this. But this week, I just tell you the algorithms because I see this, at least some of you have not learned the data structure and the algorithm. So you can just copy this, and next week I will elaborate more on this. Okay, so I think that's all for today's section. A little bit rushed in it finally, but so sorry about that.
Before you leave, when you say natural number, do you include 0?
Natural number, good question. So I see that in some courses, they say that natural number, 0 is not a natural number, but if you take the math 405 real analysis, the professor will tell you that 0 is not a natural number. So this varies in different courses.
Okay, but what about in this course?
In this course, oh, good question. I think that's not important in this
Okay.
course. So you can just regard it start from 1.
Okay.
Yeah, never mind. And as I said, the mathematics in this course is mainly discrete mathematics. And for optimization, it is more about combinatorial optimization. I think definitely not everyone would take the combinatorial optimization class that I have recommended. So if you like, I can review my combinatorial optimization notes and tell you more about it in my following sections. So please come to my sections. Thank you.